Good evening, children. Today we are doing here aromatic hydrocarbon. You know the most simplest and the most important aromatic hydrocarbon. It is benzene. Benzene has the molecular formula C6H6, and uh, it was Kekulé, scientist Kekulé, who proposed this structure of benzene. Each carbon having a hydrogen, and carbon-carbon is a double bond at alternate position. This is what Kekulé has proposed the structure of benzene. So the bond line notation for this, bond line notation of this will be so this is the Kekulé structure of benzene. Now there is a problem with this structure because you see suppose we consider 1,2 dibromobenzene. This is 1,2 dibromobenzene. According to Kekulé structure, there should be two type of 1,2 dibromobenzene. This is one type, and another type is so you see here between the bromine there is a double bond. Here between the bromine there is a single bond. So this, according to Kekulé, these two should be different. These two should be different, but in actual practice we get only one, two 1,2 dibromobenzene. So we get only one 1,2 dibromobenzene. Now these two are not possible. We don't get two types of 1,2 dibromobenzene. We get only one type of 1,2 dibromobenzene. And that means this Kekulé structure, has got some limitation. Anyway, let us consider the structure of benzene from valence bond theory. So structure of benzene from valence bond theory, and carbon has atomic number of 6. Its configuration is 1s2, 2s2, 2px1, 2py1, and in terms of box it is like 2s has 2 electron, and 2p 1 has 1 electron, this has 1 electron, this is empty. Now it is said that carbon goes to the excited state. In the excited state, this electron goes here. So excited state configuration becomes one electron here. So this is what we get in the excited state. And carbon in benzene, it is sp2 hybridized. So this s orbital px and py, it takes part in mixing, whereas this pz remains unhybridized. So the orbital which takes part in mixing, okay, it is s orbital, then px takes part in mixing, and py. So these three orbitals takes part in mixing, and we get three hybrid orbital, and the three hybrid orbital will naturally be, they should have an angle of 120 degree between them. So first let me place the 6 atoms of carbon. 1, 2, 3, 4, 5, 6. The 6 atoms of carbon, and like each carbon, is sp2 hybridized. So this is one sp2, and its smaller lobe. This is one sp2, its smaller lobe. This is another sp2, its smaller lobe. This is a one carbon atom, and like this it is there for all the carbon atoms. So one sp2 which is smaller lobe, one sp2 with a smaller lobe, one sp2 with a smaller lobe. This one is sp2 with smaller lobe, sp2 with a smaller lobe. This sp2 with a smaller lobe. So this carbon is sp2 with a smaller lobe. This is sp2 with a smaller lobe, and this is sp2 with a smaller lobe. Then again with this carbon, this is sp2 with a smaller lobe. This is sp2 with a smaller lobe. This is sp2 with a smaller lobe. Same with this carbon, sp2 with a smaller lobe, sp2 with a smaller lobe, sp2 with a smaller lobe. So you see already in between carbon and carbon bond has been formed. Carbon-carbon sigma bond has been formed. Carbon-carbon sigma bond. This sigma bond we can call it as sp2 sigma, and this overlaps with oneness of hydrogen. 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 So far, what bonds we have got, that I am doing it here. We have got carbon bond carbon. We have got all these bonds we have got, and this is also bond with hydrogen. All these bonds we have got. Now this PZ, which is unhybridized, it is there on each carbon atom. Let me draw that PZ. This is one PZ on this carbon atom. This is a 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 PZ on this carbon atom. So let me number this carbon atom. Suppose this is 1, 2, 3, 4, 5 and 6 carbon atoms. So now what will happen is, suppose this p orbital 1 and 2 sideways overlap, 1 and 2 sideways overlap, 3 and 4 sideways overlap, 5 and 6 sideways overlap. Okay, so 1 and 2 sideways overlapping, then 3 and 4 sideways overlapping, then 5 and 6 sideways overlapping. So what will happen is we will get this one. So 1, 2 sideways overlapping. This is 1 and this is 2. Then 3, 4 sideways overlapping. This is 3. This is 4. Then 5, 6 sideways overlapping. So from here we get, you can write this bond line notation for benzene. There is a double bond here, there is a double bond here, there is a double bond here. Now it is said, next it is said that not 1, 2, it can be 2 and 3. 2 and 3, sidewise overlapping. Then it can be 4 and 5 sideways overlapping, and then it can be 1 and 6 sideways overlapping. So if we consider this thing, then so let me number it. So this is say 1, this is 2, this is 3, this is 4, this is 5, this is 6. So 2 and 3. So pi bond here. Then 4 and 5, a pi bond here. And 1 and 6, a pi bond here. So this gives rise to this one. So now it has been argued that benzene actually is neither this one nor this one. Benzene is neither this one nor this one. What actually happens is that what actually happens is that this benzene, suppose, what actually happens, it is said that there is simultaneous overlapping like this one overlaps with 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 this one, and this one overlaps with this one. And similarly the lower lobe also, this one overlapping with this one, this one. So if the bond line notation, if I am drawing out this one, then I am drawing it here, then it becomes like this. So you see there is simultaneous, so it's overlapping, here we will get like this. That means, like here this bond, this bond means that carbon-carbon bond is not a single bond, it is not also a double bond, it has a double bond character, it has a double bond character. Means this bond is stronger than single bond but weaker than double bond, and this is the actual benzene, it is said. This is the actual benzene. That means benzene is not this one, benzene is not this one, this is the actual benzene. So we can see that we can see that these two actually are the resonating structure or canonical structure or contributing structure for benzene. And so these are, from here to here we can say resonance is taking place, and this is what it is obtained. And in book you will find it is not generally drawn like this. In books benzene is represented like this. So in benzene, what we see is that there is a pi cloud. There is a pi cloud above the hexagonal ring, and there is a pi cloud below the hexagonal ring. In this structure you will find in NCERT book. Let me try to draw that pi cloud. If this is the benzene ring, there is a pi cloud, above. There is a pi cloud above the ring, and there is also a pi cloud below the ring. There is a pi cloud below the ring, and that is benzene. Now, as far as chemical property is concerned, it is seen that benzene is quite stable. Benzene doesn't undergo addition reaction, and benzene undergoes mostly substitution reaction. since benzene does not undergo addition reaction, benzene undergoes substitution reaction, we are getting this support that this is in benzene. These carbon-carbon bonds are not actual double bond. These bonds are having double bond character. If it was actual double bond, then it would have undergone addition reaction. Benzene does not undergo addition reaction readily, but benzene undergoes substitution reaction. So now I will be discussing substitution reaction for benzene. Okay, so benzene undergoes reaction in this way. Suppose this is benzene. Now, benzene is electrophile or nucleophile. That we have to know first. Since benzene has a pi electron cloud above the hexagonal ring and one below the hexagonal ring, benzene is rich in electron. That means benzene will act as nucleophile. Species which are rich in electron are called nucleophile. So, an electrophile, say E plus, this is poor in electron. So this one will attack. This one will attack here. Why it will attack here? Because this is poor in electron and this is rich in electron. So how there occurs attack? This E plus comes here, and since it is poor in electron, benzene provides the electron for formation of bond. This electron goes here and this one comes here. It is like you have studied electromagnetic effect. So after this, what happens is no change in this bond, no change in this bond. Here, this one opens up. Here, E gets attached, and here there is also a bond with hydrogen that we can show it now. And this carbon, will become plus. So this is what happens. And in the next step, what will happen is this bond shifts here. This bond shifts here, and this H comes out as H plus. This comes out as H plus. That I am writing here minus H plus. This bond is coming here, so this H comes out as H plus. And we get the product. This is what we get the product. So this is a substitution product. You can see what has happened here is that this H has gone out and in its position E has come. So it is a substitution reaction. Now it is substitution reaction can be of two types: nucleophilic substitution reaction and electrophilic substitution reaction. And this substitution which benzene undergoes, it is electrophilic. It is electrophilic substitution reaction. So you should remember this thing, that benzene undergoes electrophilic substitution reaction. Why it is called electrophilic substitution reaction? Because an electrophile is going into the ring, and in its place another electrophile, that is H plus, comes out. So one electrophile is getting inside, another electrophile is coming outside. That's why it is called electrophilic substitution reaction. A question may come, why benzene undergoes electrophilic substitution reaction easily or readily. Okay, the reason for this is that benzene is a molecule which is rich in electron. Since it is rich in electron, and that's why it will behave as a nucleophile, and if it is a nucleophile, then electrophile, which is poor in electron, will easily attack. Electrophile which are poor in electron always looks for sites where there are more electrons. So that's why this one will attack here. Now we will be discussing different electrophilic substitution reaction in our subsequent video. Before conclusion, let me tell you is that this is a intermediate. This is an intermediate, and this is stabilized. It has got some stability. This is it has got some stability that can be understood. The fact that this intermediates are though highly unstable, but nevertheless it has got some stability because of this resonance that I am going to draw here. So in its resonating structure, I am starting from here. Starting from here, what will happen is in the first structure, this bond will shift here. This bond will shift here, and we will get this one, and the plus will be here. In the next structure, what will happen is this bond will shift here. Electron will move towards positive region. So it will become this one will come here. So here it will become a positive center. So this intermediate, it is stable. It is stable. We can understand from all this resonating structure. And since this intermediate is stable, that's why this is formed, and from here we get the product. So this much we'll do today. In the subsequent video, I will be telling you about different types of electrophilic substitution reaction of benzene. One is called halogenation, one is called nitration. We'll discuss about sulfonation. We'll discuss about Friedel-Crafts reaction. Friedel-Crafts reactions are of two types: Friedel-Crafts alkylation, Friedel-Crafts acylation, and so on. So this much for now. This much for now, and we will be doing those reactions in the next class. Till then, good night.